welcome back, everybody. And feel free to continue, Po-Ling.
Okay, great. So I think I fixed the issue with the fees earlier. Let me just say something really quick. So assuming I didn't make a mistake in the fix, the problem was that we wanted to apply a fee to both sides of this. And there was a factor of 2, which was offending us. So I think if you, well, in our application of Fano's method, we start with this minimax risk. We had expectation of L, which is written explicitly as phi of rho. So I think if we move the 2 down to the denominator and apply phi, and then just do the appropriate algebraic manipulations, because we can apply Markov with whatever we want, then I think it all ends up working out. So we can massage things so that we have rho is bigger than 2 delta, which is what we wanted. So what this ends up doing, and I wrote it in blue, is before we had 0.4 phi of 2 delta, and now it becomes 0.8 phi of delta. So the good news is that we can, in fact, apply this to more than just the loss function being a metric, being a semi-metric. All right. So going back to this local differential privacy, and we have this monster expression here. So what I want to do now is just go through one example. I think what this example will show is why this distance-based notion of Fano is useful. So and I kind of hinted at, in order to prove this theorem, which we won't have time to go through, the 2 steps are to use the distance-based version of Fano and also upper bound the mutual information using an appropriate quantity that depends on alpha as well as some other stuff. But we could just use the not distance-based version of Fano, right? Like as long as we make sure that we start with a 2 delta separated set, things should be okay. The reason for the distance-based version of Fano is that it might be easier to construct some sort of a set, which is a subset of our distribution set, which we don't enforce to be 2 delta separated just for the computations. So we'll see this in the example that we're about to do. And I'll talk more about this quantity. I guess this phi of v, which is showing up, is probably mysterious because I haven't had a chance to go through the proof with you, but we'll at least show how to evaluate it for the set that we'll construct to work on. Okay, so, and my plan is to spend about 15 more minutes, maybe at most, on this, and then switch over to the computation to finish it off. So the example is mean estimation. All right, and we're going to depart a little bit from our parametric parametric classes that we dealt with earlier. So here, let script P be the class of p-dimensional distributions supported on a ball. Supported on the ball of radius r in Euclidean norm. And we will show that for alpha between 0 and 1, we have the locally differential private risk in squared 2 norm is equal to omega of r squared p over n alpha squared. Okay. And just a short note, so maybe 2 remarks. So this is achievable using a sampling mechanism described in Ducci. So I'm not going to go through the details of it because it's a bit complicated even to state. I mean, I can't just say this is achievable using the sample mean, like you would expect, because I mean, you would expect from the previous lectures, because the sample mean, of course, is not going to be locally differential private. So what you have to do is construct a way of generating the ZIs and then construct an estimator based on the ZIs, and that itself is rather complicated. But this lower bound is in fact achievable. But maybe the one thing to remark on that carries a bit of information is that comparing this to the non-private Minimax risk of theta of r squared over n, the effective sample size goes from being n to being n alpha squared over p. Okay. So this is a smaller quantity than n. So because we want to enforce privacy, then we do in fact lose something, and rather than additive factor, now it's a multiplicative factor. Okay, so let's discuss the proof. So let script v be the vertices of the p-dimensional hypercube, which is -1 + 1 to the p. Okay. And then for v in script v, define the distribution PV such that x distributed as PV is generated by drawing an index j in the set 1 through p uniformly at random. And then setting x to be equal to r ej. So ej is the canonical basis vector with probability 1 plus delta v transpose ej over 2 and negative r ej with probability 1 minus delta v transpose ej over 2. Okay, so this is a particular 2-point distribution for each value of, sorry, it's not going to be a 2-point distribution because x could be actually anything of the 2p possible values. So x takes values in x equals plus or minus r times ej, where j goes from 1 to n. Okay. So it's kind of biasing the choice. It's biasing the values that x is taking according to the coordinates of v. So for every distribution on this, or for every v in this hypercube, we have a different distribution, right? So note that PV is indeed supported on V2R, obviously, because all the possible values are going to be multiples of the canonical basis vectors. Okay, and a couple other things to note. So now note that, so really this is the construction, and now what I'm going to do is I'm going to calculate the various quantities that are showing up in Fano's method. We need to calculate the separation function and the size of the neighborhoods. So the first thing to note is that expectation under PV of x is equal to 1 over p times, or okay, so if we wanted to look at just the jth, or here, hang on, sorry. It's not what I meant to say. So note that theta sub v, which is the parameter that corresponds to the mean of the distribution, is equal to delta r over p times v. And if you want to see this slowly, then if you look at the expectation under PV of the jth coordinate, it's equal to 1 over p times r times 1 plus 1 plus delta v transpose e j over 2 minus r times 1 minus delta v transpose ej over 2. And you can check that this is in fact equal to delta r v transpose ej over p. Okay. So now we need to look at these separations. So remember, we have some sort of a metric that's defined on the v's themselves. So let this be the L1 distance. Then for t bigger than 0, we have the separation function is equal to, well, it was 1/2 of the minimum of the distance between the two thetas when the metric between the v's was bigger than t. So if I square the 1/2, I get a 1/4. and we have a minimum of theta v minus theta v prime 2 norms squared, such that v minus v prime in 1 norm is bigger than or equal to t. So just to reiterate, I can define this, this metric that I'm using to define distances between the v's however I want. I'm choosing it to be the L1 distance. And the separation function is 1/2, which I now square, of the distance in terms of row of the thetas squared. Okay, and because I have calculated this thing up here, I can conveniently plug it down there. So this is equal to r squared delta squared over 4p squared, minimum of v minus v prime 2 norms squared, such that v minus v prime is bigger than t. And then now I have a nice convenient relationship between 1 norms and 2 norms. This is bigger than or equal to r squared delta squared over 4p squared times t over square root of p squared, which is equal to r squared delta squared t squared over 4p cubed. Okay, so I've calculated my, my separation function. Now I need to calculate the neighborhood size. So I can take whatever t I want, and for the rest of this, we're going to take t equals p over 6. So you can calculate the neighborhood size to be equal to the sum s goes from 0 to t of p choose s. Why is this? Well, it's basically because, remember, the neighborhood size is in terms of the v's, how close are, how many points are within some ball. And these v's were all on the vertices of a hypercube. So it's really just, it's a combinatorial problem. How many coordinates do I change? And you can bound this using standard techniques. This is bounded by 2p choose t, which is bounded by twice pe over t to the t. And this is equal to, so plugging in here the fact that that t is p over 6, we get some cancellation, and this is just 2 times 6e to the p over 6. Okay, so what we're interested in is log base 2 of the size of v over nt. That's what shows up in Fano's inequality. And this is going to be bigger than or equal to, so the size of v is 2 to the p, and we have log of that is p minus p over 6 log base 2 of 6e minus 1, which is bigger than or equal to some constant times p. That's what we want. We want order of p. Okay, so we've calculated our distance function, our separation function. We've calculated this quantity, the number of points in the set, rescaled by the neighborhood size, and now we need to worry about this monster here, right? So this thing. So let's. I'm not going to do the calculation completely. I just want to say a couple of things. Maybe I will, yeah, let's go back down here. Okay, so next we show that 1 over the size of v times supremum over this guy of sum v in v, phi v squared of gamma is less than or equal to some constant times delta squared over p. Okay, and the way we do this is by writing the left-hand side as a quadratic form in gamma. What's gamma? Well, gamma is a function. So note that gamma, which was in a function defined on script x, can be represented as a vector in r to the 2p. Okay, so so this notation here means that it's a bounded function defined on the space of x. And remember that x itself could only take on 2p possible values, right? They were all of these plus or minus r ej's. So I can write out I can represent a function as a 2p dimensional vector, which just tells me what every coordinate is. And it turns out that actually, well, I should say if you ignore this supremum part, this quantity here can be written as a quadratic form in gamma. So how do we do this? Well, roughly speaking, so we have, so here's rewriting the definition of phi v. This is expectation under PV of gamma of x minus 1 over the size. So this is sort of the average value. Expectation under PV of gamma of x. Okay. So this is the definition. And now you can calculate that expectation under PV of gamma of x. Well, what's that? Well, it's the sum j goes from 1 to p. So this is just by directly writing out what it means to be an expectation. So the value is either r ej or r minus ej. The probability is 1 over p times 1 plus delta v transpose ej over 2 plus gamma of negative r ej. And the probability of that is 1 over p, 1 minus delta v transpose ej over 2. Okay, so this is just by directly writing out what this guy is. So then by our construction of script v, we can also check that phi v of delta of gamma is equal to delta over 2p times summation of j goes from 1 to p, gamma of r ej times v transpose ej minus gamma of negative r ej times v transpose ej. Okay, so where is this coming from? It's not actually that mysterious. So my claim was that we can actually transform this sum of the squares as a quadratic form in gamma. So what we would really like is if we can write this guy phi v of gamma as gamma transpose something, right? We want an inner product of gamma and something else. So we write down what the first quantity is, and we have something that looks almost like an inner product of gamma and something. Well, I mean, it is. So it's a sum of gamma on each of the coordinates multiplied by something else. But it would be really nice if we could get rid of these extra terms, because what we really want is to write this as, maybe I'll write it here and then erase it. We want it to be gamma transpose times something times v. That would be really nice. And actually, the convenient thing is that the terms that are in our way, they get eliminated when I subtract out the mean over all of the v's. That's what I'm writing here. So to get from here to here, I'm just preserving the terms gamma of r ej and this delta term. I took out the delta and the 2 and the p. Okay, so I have that, and then you can write this. We'll define this as delta over 2p times gamma transpose a times b. Let's get rid of that. Okay, so now, well, then, what do I want? Well, I want, okay, so I want to calculate, I want to renormalize by, I need to sum up over the v's and renormalize by the size of v. And then by our construction, we also have 1 over the size of v, sum v in v of v transpose is equal to the identity matrix by our construction. And this is important. So this is because when we were creating this set, we chose these terms v to be on the vertices of the hypercube. So you see that if we had to constrain the vectors v so that we had some separation between any pair of distributions, then we might not have these nice properties that we can just sort of, that we can demean this quantity when we subtract out that, and that we can just make the v's evaporate. Okay, so overall, we can bound the summation of vv of gamma squared. Let's put a 1 over v in front of it, using spectral properties of the matrix A. Okay, so if you actually write out what is this matrix A that falls out of this representation, then it's a very simple matrix, and you'll find that that things cancel out. So overall, we end up with a bound on the order of delta squared over p. And you can see that sort of if you square this guy, you have a delta squared over p squared. And the reason why a p gets knocked off is because we're taking a supremum over gammas which are bounded in infinity norm. And when we talk about spectral properties of a matrix, we're bounding quadratic forms where gamma is a unit vector. Okay, but we won't dwell on this longer. So, oops, didn't mean to do that. So combining the results, we finally have R sub LDP of R 2 norm squared and alpha should be equal to omega of. So we need to take our what is it? So we need to take our separation function. That's the first thing that shows up. Take our separation function. So we have an R squared delta squared P squared over, let's see, over P cubed times 1 minus n e to the alpha minus 1 squared times constant delta squared over P over CP. I guess there's an extra factor of P that shows up. Where is this? Oh, right. R squared delta squared. Oh, yeah, okay, sorry. So our separation function was R squared delta squared T squared over 4P cubed. And we chose T to be of the order of P. If you remember, T was P over 6. So altogether we get R squared delta squared P squared over 4P cubed, which is what I've written here. And then the bound has 1 minus this guy. Here, this is the bound that we just derived from up here. And then we had a bound on the log of the set, which was CP. Okay, so we put it all together. This is omega of R squared delta squared over P times 1 minus 3C prime alpha squared n delta squared over CP squared. Since e to the alpha minus 1 quantity squared is bounded by 3 alpha squared for alpha between 0 and 1. And then, so now we play this, the usual game. How do we make this order of 1/2? Then we take delta squared to be on the order of P squared over alpha squared n. So our LDP is going to be equal to omega of R squared P over alpha squared. Okay, so we're done. All right, so hopefully this wasn't too laborious, but I hope that this kind of illustrates, well, first of all, of course, how you would get these lower bounds for local differential privacy, but also what the benefit is of using the distance-based Fano method, where you can just define this the subset of distributions however you want. Okay, and maybe one final note before I go to computation. I just wanted to say that there's one other method that I'm aware of for bounds on estimators that satisfy privacy. So another method for establishing lower bounds under DP is using a method of tracing attacks. And this is work that's been pioneered by Dork et al. 2015. And the idea is to construct an algorithm which can detect the absence or presence of a data point X in the target set X by looking at an estimator, theta hat of X. And this might be possible if theta hat of X is accurate enough, providing a lower bound on the accuracy of private estimators. Okay, so if we have the guarantee of privacy, that means that that nobody should be able to tell based on theta hat whether or not a particular data point is in your set. So just very, very briefly to give you an idea of it. So this method has been used in the statistical literature by Tsai et al. In 2020 to study high dimensional private mean estimation. And also linear regression. Okay, and as an example, actually this is an oversimplified example, what would a tracing attack look like? So a tracing attack for mean estimation might look something like this. A sub mu of x theta hat of capital X. So this is supposed to tell us whether or not the datum little x was used to construct theta hat of x. And if we define this to be equal to x minus mu inner product with theta hat of x, okay, then this succeeds if theta hat of x is close to the empirical mean. So this is sort of a massive oversimplification, but you can imagine that if you replace this estimator by the sample mean, then if little x is equal to if it's not equal to one of the xi's, then this will be very close to 0. However, if little x happens to be one of the xi's, then we can detect a correlation that x is present in the data. Now, of course, this is only true if theta hat is exactly equal to the mean. However, this also tells us that if theta hat is close enough to the mean, then this tracing attack should be able to succeed in telling you whether or not little x is there and therefore violate privacy. And therefore, a private estimate cannot be too close to the mean and therefore cannot be too close to the true mean mu. Okay, so that's that. So now in the final half hour or so, let's see how much time I've given myself to talk about computation.
Like, can I ask a quick question?
Yeah. Go ahead.
Yeah, so I'm curious. So this works even in situations where Fano's inequality fails?
I haven't looked in too much detail, but I think that this might lead to tighter bounds than Fano's inequality would. But I haven't specifically tried to check what Fano's inequality would do in these particular cases.
Very cool, thanks.
Mm-hmm. Okay. Great. So lastly, we have computation. And as I said, I'm going to be a bit brief here because I think a lot of the other talks are on computation. And secondly, I'm not really a complexity theorist. So yeah, so I'll just kind of give big picture ideas of what the result here is, what the result is here, and also what the ideas of the proof are. Okay, so the reference that we're going to go off of is Zhang, Wainwright, and Jordan. So this is Yu-Chen Zhang's work from a couple of years back. And the paper is lower bounds on the performance of polynomial time algorithms for sparse linear regression. And this is a paper from 2014. Okay, so this is kind of bringing us full circle to the first lecture when we talked about linear regression and we had lower bounds. So the problem setup is that we have the linear model, y equals x theta plus w, where w is this independent Gaussian noise and x is fixed. Okay, and we assume that the true theta is in r to the p and is k-sparse. Okay, so we are looking at the minimax risk, which is in the prediction error, infimum over theta hat supremum over all sparse vectors of 1 over n expectation of x theta hat minus x theta 2 norm squared. Okay. That look a little bit nicer. Okay. So this work shows that the risk is strictly larger, or the minimax risk is strictly larger when theta hat is constrained to the class of polynomial time estimators. Okay. I should also say when X comes from a certain class of matrices. Okay, so as in the first lecture, we went through a lower bound, and I said that in fact it's achieved when we use the lasso estimator, which is certainly a polynomial time estimator. The point now is that we're going to relax the conditions on X that we had imposed in the first lecture. So just to make a couple more comments before I state the theorem. So an upper bound of the form order of sigma squared k log p over n can be achieved by taking the estimator theta hat is equal to the arg min over theta in the sparse ball. So look at all k sparse vectors, y minus x theta 2 norm squared. And this is a result of Bunia et al. 2007. But the estimator is computationally intractable, because it involves searching over all possible sparse vectors. So instead, we often consider the lasso estimator. Theta hat is equal to arg min over theta in Rp of 1 over n y minus x theta 2 norm squared plus lambda theta 1 norm, where we choose lambda appropriately. So now this ends up doing well as long as X is a well-conditioned matrix. So to kind of reiterate these ideas, so let gamma of X denote the restricted eigenvalue, or in high dimensional statistics speak, RE condition, constant. This is the function of X rather than a condition. Constant of the matrix X. So this means that gamma of X is the largest gamma such that 1 over n times x theta 2 norm squared is bigger than or equal to gamma theta 2 norm squared for all theta which are in a particular set. And this set is the union over all subsets of size k of this cone set C of S, where C of S is equal to theta in, oops, that shouldn't have happened, theta in Rp, such that theta SC, this is the L1 norm on the elements that are not in S, is less than or equal to theta S. Oops. Okay, so this is a bit of a mouthful, but this is kind of this standard theory for those of you who work in high dimensional statistics. So you want, it's kind of like a sparse eigenvalue lower condition, and that's how we stated it in the first lecture when we imposed conditions on X. So you certainly want that X is well conditioned when you multiply it by sparse vectors. But this set is a little bit bigger than just all of the k-sparse vectors. So the k-sparse vectors would certainly have the one norm of the off support guys less than the one norm on everything else, because this is equal to 0. But we have a slightly bigger set here, and we want this to hold here. Okay, so under an upper bound, so under what's called the column normalization, condition which is x theta 2 norms squared over n is less than or equal to theta 2 norms squared for all sparse vectors. Now here we're in the 2K ball. The lasso satisfies the upper bound, supremum over all k sparse vectors, 1 over n expectation of x theta hat minus x theta 2 norms squared is less than or equal to constant over gamma squared x, sigma squared k log p over. Okay, so so just to contrast these two guys, so the upper bound that I stated earlier here for the computationally intractable estimator has a sigma squared k log p over n. Lasso does as well, but we have to assume that it's well conditioned, or at least the theory holds under an assumption that the restricted eigenvalue constant is not too small. So the way that we stated it in the first lecture was we said that there was some constant lower bound on the sparse eigenvalues. So you can kind of think about it like this too. So the guarantees of the lasso get worse if x is badly conditioned. And you know, why do we think about this as not necessarily a constant? Well, let me just remind you. So x is in r to the n by p. And if you think about x as being drawn from some ensemble, let's say normal 0 sigma, then gamma of x is kind of like the minimum eigenvalue of sigma. And you can make the minimum eigenvalue of sigma get smaller and smaller as the problem grows. Okay, so the question that we want to ask is, do computationally tractable estimators exist? Which avoid the factor of gamma of x in the denominator. Okay, and the main result is that the answer is no. So this is the result of Zhang et al. All right, so so sort of colloquially, the extra factor of gamma of x is actually, it's a little bit stronger than that. The extra factor of 1 over gamma squared of x is unavoidable in all polynomial time estimators, assuming a particular conjecture in complexity theory, which is that NP is not a subset of P poly. Okay, and P poly is the set of problems solvable in polynomial time with the help of an advice string, which can depend on the length of the input. I should say with the help of and is polynomial in length. Okay, so just a tiny bit about the complexity theory. So P is a set of problems that are solvable in polynomial time. It turns out that P is actually a subset, but not is a strict subset of P poly. So there are some more problems in the set P poly, because in addition to being, well, so P means that it has to be polynomial time just in the inputs. P poly gets some side information. So there's a pre-computed string that it can use as an input, as a side input based on the size of your problem. So it is, I'm not going to go into too much detail here. So this is known, and this is conjectured. Okay. So assuming that this is true, we have the following result. Theorem says that consider any polynomial time algorithm which outputs k-sparse estimator theta hat, then for any delta in 0, 1 and gamma sufficiently small, there exists NPK and a matrix X in R to the n by P, such that, and here I'm being a little bit loose, so gamma of X is going to be approximately equal to gamma, and supremum over all sparse vectors of 1 over n, expectation of x theta hat minus x theta, 2 norms squared, is lower bounded by a constant over gamma squared times sigma squared k to the 1 minus delta log of p over n. Okay, so a couple remarks. So the first remark is that, maybe I'll write this down. So the first remark is that gamma can be chosen arbitrarily small. Okay, and this falls out of the proof, although the proof is rather complicated. And then if gamma and k are fixed, construction of a bad matrix X exists, exists for n and p sufficiently large. So it's not just saying that there exists a particular dimensionality that works. In fact, any dimensionality bigger than that will work. And then the other remark is that since delta is between 0 and 1 is arbitrary, the right-hand side can be made, well, maybe not exactly arbitrarily, but quite close to k squared, or not k squared, to k log p over n, which is what we got from the lasso. I should put the gamma in there too. Over gamma squared. Okay. I feel like there was one more thing I wanted to say, but maybe not. So this is saying that, so in some sense, this, yeah, question?
I'm sorry, yeah, so I guess one remark, maybe meaning to say this, but the condition that theta hat is k sparse is important for the result. And I believe it's still totally open whether there exists an estimator theta hat without the restriction that it's k sparse that achieves a good rate.
Yeah, so I was reading up on this last week and I saw a follow-up paper from a year or two later. I can't remember who the authors were, but they were studying that problem. I don't really know what the conclusion was. But at least, yeah, as of the time of this paper, it was certainly a restriction. I think there was at least one paper that attempted to relax that. Yeah. Okay, so, and then maybe the last remark is you might be wondering, like, what does this mean approximately equal to? So I'm not going to go into the details of this, but in some sense, you have to be a little bit more careful than I'm even going to talk about. So when you talk about a polynomial time algorithm, it's in the length of your input. But these are all real valued matrices. So we need to do some discretization in order to represent it as a bit string. And this is kind of with respect to the discretization. So we can make it as close as we want with respect to the discretization that we use to make this rigorous. Okay, so my goal in the next...
We have a quick question.
Oh, sure.
So, Lee, can you clarify the quantifier over k? I mean, because in the theorem statement, it seems that for every gamma there exists k, but then later on you say that for any fixed gamma k, can I mean, do you have
yeah.
Gamma, or can you get the lower bound for any gamma and k just choosing n and p large enough?
So I don't remember the details of the proof well enough, but definitely for every gamma there exists a k, and for both of those there exists n and p large enough. I mean, if n and p are large enough as a function of gamma and k, then it's true. But yeah, I don't quite remember whether it's for all k or just a particular k. Yeah.
Okay, thank you.
Okay, good. So now in the last 15 minutes, I'm just going to give you sort of broad strokes what the idea of the proof is. Okay, so the idea of the proof is to So consider a particular NP hard problem involving solving a linear system to a certain accuracy. And the NP hard problem is a linear algebraic version of the exact 3-set cover problem. Okay, and the exact 3-set cover problem is the following. Given an integer m greater than or equal to 3, a set S, which is defined as 1 up to m, and a collection script C of 3-element subsets of S, find m over 3 subsets which exactly cover S, assuming such a cover exists. Okay, so this is known to be an NP hard problem, which means that it's at least as hard as all the hardest problems in the class NP. And a solution, so first I'm going to use words and then I'll state things a little bit more explicitly. So a solution to the linear system can then be used to obtain a solution of the exact cover problem. And then the NP hardness of the latter, together with the conjecture that NP is not contained in P poly, implies a lower bound on the prediction error of any polynomial time algorithm. Okay, and this is the prediction error of any polynomial time algorithm, which solves this linear system that's used for exact cover. And then the last step is then we construct a design matrix X such that accurately, or I'll just say such that small prediction error for solving the system x theta. I should say design a matrix X and also theta such that small prediction error for the system x theta implies small prediction error for the exact cover system. Okay, so that's roughly where we're going. Solving this linear algebraic version of the exact cover problem is going to be hard. So we have a lower bound in the prediction error. We'll show how to go from the exact cover problem to the original high dimensional regression problem and bound the prediction error of the first by the second. So just a couple more details. Okay, so here's some more details. There's this first lemma, and the lemma says, given an integer m, let L be equal to m choose 3, then we can construct, and this is an explicit construction, a matrix M, which is in -1, 0, 1 to the m plus 3L by 4L, and an associated set of vectors script V is equal to the set of V in R to the m plus 3L, such that V is equal to mu for some u in the set 0, 1 to the 4L intersect the sparse ball. and we'll denote this as U. Oops. Such that the following problem is NP hard. Given any vector v in script v, compute u in script u such that mu minus v is bounded by 1/2. Okay, so this is the linear algebraic problem that if we can solve this to the desired accuracy, which ends up being 1/2, then what can be extracted from this is a solution to the exact cover problem. And I won't go through the details of this. The point is that the same matrix M works regardless of the set cover problem. Okay, so I'll just say here that NP hardness comes from the fact that any set cover problem S script C can be used to construct a response vector U, and I guess I mean predictive vector. Oh, okay, I just mean vector. I guess that's the prediction vector. We can construct a vector U in script U, and the related vector V equals mu, such that an approximate solution of the linear system would solve the set cover. Okay, so now I have a linear algebraic problem, which is an NP-hard problem. Okay, so then the next lemma is the following. So I'm writing this in a little bit more concreteness. So let f, g, and h be arbitrary polynomial functions. Then for an integer m0 bigger than or equal to 1, there exists m bigger than m0 and a distribution, let's call it Q, over the set of U, such that any solver U hat, which can be encoded in f of m bits and terminates in g of m time, satisfies probability that U is coming from U, mu hat minus mu, 2 norm less than 1/2 is bounded by 1 over h of m. Okay, so here I'm being a little bit more explicit. Really, you can think about U hat, which can be encoded in f of m bits and terminates in g of m time, as our notion of polynomial time algorithm. This is, remember, we want to, the hard problem was solving the exact cover problem to an accuracy of 1/2. And this says that there's some ensemble over the set of possible U's, so that the probability of being accurate is going to be as small as we want it to be. And the important thing here is that the same ensemble Q works for any algorithm U hat. Okay, so I mean, because it's an NP-hard problem, then for any estimator, for any algorithm U hat, there should be some hard instances. And this result says that, in fact, there are some hard instances that are hard for any U hat. And the proof here depends on the NP is not a subset of P-Poly conjecture. So I won't go through the details here either. I guess this is very much in the complexity theorist side of things. And basically, because of, well, assuming that this conjecture is true, then we can turn the NP hardness statement about a deterministic problem into a probabilistic statement. So then the last bit, which I'm just going to highlight briefly, is finally, for any x and any estimator, theta hat, we write the bound supremum over all k-sparse vectors. And now this is the quantity that we were after in the first place. This is bigger than or equal to. So now we're going to take an expectation over a particular set. So this is r theta is distributed as q of x theta hat minus x theta 2 norm squared. Okay, so maybe I should say that this is sort of a double expectation. So on the left-hand side, we're looking at a supremum over all possible choices of theta. And here we're saying that the supremum is lower bounded by an average. And in the average, we're drawing theta randomly from an ensemble. And then there's also the original expectation, which was over the generation of the response vector y, which leads to randomness in theta hat. Okay, so this is a double expectation, but we're really bounding the supremum by an average. And the reason why we can do this is that we need theta to be k-sparse. And the way that we defined the set U for which Q is defined is that it's actually also going to be a k-sparse. It's a sparse set. The sparsity is m over 3 plus L. So this holds if k is at least m over 3 plus L. Okay, so we have this lower bound here. And what's the R for? This is just a scaling factor, which will be determined, or which is chosen later. And maybe the other thing to say is R is related to gamma. Okay, so I mean, I want this to hold for any k-sparse vector. So of course, if I scale them by anything I want, it's okay. And remember that the statement of the theorem was that I have a fixed gamma and I want to construct an x such that gamma of x is approximately gamma, and the lower bound also holds. Okay, so lastly, we show how to construct, or I won't show you, but it's in the paper. So construct x in r to the n by p from m and gamma, such that first of all, gamma of x should be approximately equal to gamma. And secondly, this is I and this is I. The right-hand side of, let's call this star, can be lower bounded by the prediction error of the problem that involved U. Okay, so we have a way of constructing x from m. I mean, it's some sort of block matrix construction where there are lots of m's living inside of it, and one can show that with this construction we can lower bound this guy by this guy, and that's approximately true. There are some other things that are hiding here. So there's going to be, well, this is true for, of course, any algorithm U hat. And also there's some prefactor that depends on n, p, k, and r. Okay, so finally, and I know this is kind of loose. So finally, we lower bound expectations by probabilities, right? So some version of Markov's inequality then allows us to lower bound the expectation by this probability of error. So then use the lemma to lower bound the last expectation. Okay, and if you're curious, well, you know, we were looking for a bound that was of the form k times log p over n. So that's coming out of this part, the k times log p over n. We were also expecting a gamma squared to show up in the denominator. Well, in some sense, r times theta corresponds to u. And so what comes out of all of this is an extra factor of 1 over r squared. And that 1 over r squared roughly is what gives you the 1 over gamma squared. Okay, so that's what I wanted to say about this proof. So just to review, the main steps, as I had outlined up above, were to look at this NP hard problem of the exact cover problem, to turn it into a linear system. And the linear system looks like this. So we solve the problem of mu minus v up to a desired accuracy. And because of the NP hardness of the exact cover problem, this problem has to be hard. So the probability of having a prediction error bounded by 1/2 should be small. And then we need to find a way to go from this linear system to constructing a linear system involving where we design x, and we need the restricted eigenvalue constant to be close to gamma, And then the last part is to relate the two prediction errors. So I'll stop here and happy to take any questions.
Great, thanks, Po-Ling. Any questions that I can give the mic to the asker?
Hey, I have a question. Can you hear me? It's Adam Clevens.
Yeah.
Mhm.
Hey, Po-Ling. Thanks for your talks. They're very thorough. Does this lower bound rule out, say, an algorithm that has running time like k squared log n, or anything larger than k, like k log n, or?
Running time, or you mean
Or sample complexity? I mean,
bound? Yeah, you mean this bound here, right?
yeah. Like you could still hope for k log k or something, I guess, right?
Yeah, that's true. Yeah.
Okay, and then just a more of a comment than a question, but I think like the example you gave about Gaussians being ill-conditioned, I think for the specific case of Gaussians, we have upper bounds on the sample complexity that are independent of the condition number, because like the Gaussianity actually buys you something there, and you can hope for. We don't have efficient algorithms for that yet, but the sample complexity is independent of the condition number of the covariance matrix.
I see.
So it doesn't contradict anything you've written. It's just for the example you gave for Gaussians, I don't think these bounds apply.
But I guess I was just giving an example of how the bound the gamma of x quantity could get small as n and p grow.
Right.
And so I mean, if you just, it's true that if you have, well, I mean, like if you look at Gaussians, which are distributed according to like an ensemble like this, and you make the minimum eigenvalue of sigma go to 0 with p, then wouldn't that cause this guy to get small?
Yeah, no, that's the interesting thing. For the case of Gaussians, of course, that factor does get smaller and smaller, but you can still prove an upper bound on the sample complexity that's not dependent on that term.
I see. Okay. Yeah, I'm not aware of that work, but I should read it later.
Anyway, sorry. Thanks for your talks.
Thanks, Adam, for the questions. Any other questions? Great. Well, feel free, of course, to message Po-Ling with further questions offline, and let's thank Po-Ling again for a great series of lectures.
Thanks a lot.
Great. So we'll see everybody back here in a couple of hours.